of course, starting late because I got very little sleep. I don't even remember. Yeah, I think I got the midterm done, and then I had some bugs to fix in another project, and so it just all stacked up. So, hence my complete exhaustion. But last time we did start talking about memory technology, and it was kind of fun. I enjoyed it. I hope you did too. But we went through various kinds of memory technologies. We notably skipped over solid-state drives, which are pretty important to understand. I'll just try to give you the details of those as we go through so you have a frame of reference. But we had these two principles that we discovered, which is that if you hold technology constant, then the smaller the memory is, the faster it is. And that's mainly due to physical limitations. There's less addressing logic, and there's also less distance that signals have to travel. And we can make dense memories, and we can make, I shouldn't say sparse, but we can make more or less dense memories. And the denser it is, the harder it is to sort of go and access individual values. And so that also tends to mean that denser memories are slower than less dense memories. So, and you can think about it even with a hard disk, something like a hard disk, as the memory gets larger, if I hold density the same, I hold density constant, as I make the memory larger, then the head has to slew further, or I have more platter that has to go under my head, or whatever. So you have various things that will increase as well, unless I just stack platters. So that tends to be a pretty effective technique for keeping larger disks as fast as smaller disks. So anyway, these were various things that we explored last time. And we'd like our systems to be nice. We'd like to be able to have the performance of a small memory, but we'd like to have large memories because we have a lot of data that we'd like to process. And of course, we're never going to get it if we connect the processor directly to our DRAM, which is currently our large, dense memory of choice, large, dense, cheap memory of choice, because there's a problem that the memory is getting faster, but then the processor is getting faster as well, and the distance between them is actually opening up. And this is continued even though processor speeds have not increased as rapidly as they did over the period of the chart that I showed you. So it was like up to 1998, I think, and in 2002 it kind of leveled off a bit, but it's still growing faster than DRAM performance. So we introduced the notion of caching, where instead of just satisfying each read as it comes in, we're going to read a whole chunk of data, hoping that the program is going to read other things near that value, or that it's going to read that value again. So if that works, if the program has that behavior, then yay, we start getting a memory that's nearing the performance of the smaller cache, but we still have the size of the large memory. If we have a program that doesn't access memory that way, then we have to go back and access more data, and so we end up with a program that basically has the performance of the large memory and the size of the large memory. So what we want to explore a little bit today is what program behaviors do maximize this benefit of caching, and also what are some of the design aspects of the cache. And one thing I love about Assignment 5 is that it actually forces you to implement various aspects of how a hardware cache works in a software emulator, of course, because I can't give you a piece of silicon and a chisel and say, have fun. So you get to go through and implement that stuff, and it seems to be very effective for helping people understand how it all works. Okay, so like I said, CPU reads a value from main memory, and by this I mean the program says I want this value. Then the processor goes ahead and reads neighboring values as well and loads them into a cache. And of course, we have to have programs that access memory in a specific way if we're going to actually benefit from having this cache, so that most of the accesses actually are satisfied out of the cache. And if we have a program that, for example, accesses all kinds of memory randomly, then we get no benefit from the cache, because every time we go and access a value, then it's probably not going to be in the cache, and so we have to pull another block. And then we access another random value somewhere in the memory pool, and that also is not in the cache, and so we get poor benefit from our cache. Okay, we call this behavior locality, and we say that programs have good locality or they have horrible locality, depending on how well or how badly they're going to be able to utilize the cache. So spatial locality is one kind of locality where basically you expect that if you access a particular address, you're probably going to access things around that address shortly thereafter. Think about the way that a stack frame is accessed. Okay, when you access something on the stack, you're probably going to access adjacent values pretty soon. Same thing if you're accessing array elements and so forth. Then you have temporal locality, which is when you access something, you're probably going to access it again soon. Okay, so you have spatial locality and temporal locality. Spatial locality is I'm going to access nearby stuff. Temporal locality is I'm going to access the same thing over and over again. And so if we have programs that are cache-friendly, is the way we generally describe it, then they have good locality. They either have lots of spatial locality or lots of temporal locality or hopefully both. And then the hardware is able to run them fast. And if you have a program with poor locality, then it's not going to use the caches effectively, and it is going to run slower. Okay. If you are trying to think of a good analogy to spatial locality and temporal locality, the one that is frequently used is how your web browser works. Okay. I go to the CNN website or I go to some news website, then there's certain images or certain, like the icon, the fave icon that shows in the URL bar on the browser. Those things are accessed pretty much by every page, so every page references those. And your browser has a cache, and it tries to cache local content, or I should say it tries to cache remote content locally so that it can just retrieve it from the local cache instead of having to retrieve it over the internet, because that's slower. So that would be a good example of temporal locality, because I access the same thing multiple times. Also, if I have a page and I read the page and the page has all these links to images and so forth, scripts and styles and things like that, then a good browser is going to be able to start retrieving all of those things right away because it knows that the page needs to reference all those things. So that's a good example of spatial locality. I'm accessing things that are near the page, at least in terms of links. So that's a pretty good analogy. Okay, now, it is easy to get good locality, at least if you're thinking about it. It's certainly also easy to design programs that have terrible locality. You'll see a good example of that on Assignment 5 as well. But our vector add code from, what was it, like Lecture 7 or whatever, this is a great example of good spatial and temporal locality. Okay. In fact, this is mainly spatial locality. We don't see the same thing accessed multiple times. But we access these arrays in sequential order, as people normally would. It would be really unusual for somebody to write something that traverses arrays and randomly hops all over them. I mean, it would be very unusual to write a program like that. And so the common behavior is actually already really good. So even though it is easy and common to do, it is still a good thing to understand. So this was the example that I gave from Lecture 1, where he had this array of atoms, where it's a three-dimensional array, and you may or may not already understand how C lays out arrays. We'll go through it a little bit today so that you get a sense of how multi-dimensional arrays would be laid out. But the way that it was structured was that we had the loops arranged like this, so I and j and n, and we used I and j for our dimensions, and then we used n for the atoms. And so clearly, as we access this thing, we're hopping a little bit around the array. And so when you have multi-dimensional arrays, it is a little bit easier to have poor locality. Okay? This is poor spatial locality. The reason why it has poor locality is because C lays out arrays in row major order. This is the same thing that C++ does. Many languages actually choose this. There's a few that do column major. I think that MATLAB is one notable example that lays them out in column major order. But basically, you can see that all of the elements that are adjacent to each other have the same first index value, and then that one increments. And then, so for values with the same first index value, the second index values are in order. So we have 0, 0, 0, 0, 0, 1, 0, 1. And then the third index value is after that. So basically, this is what we call row major order. And so you can see that the way that we have our loop structured, atoms n, I, j, we're kind of taking big hops through this array. And it's a large array. The number of atoms was like 10,000 or something like that. I can't remember exactly. So what are we talking? Actually, that's kind of small compared to modern memories. This program was written, I don't know, I think probably 2005, 2006. So anyway, computer systems have definitely gotten a lot more powerful. But what we can do is we can arrange these loops, so instead of jumping 4 elements each time, we can just access them in order, because the things that we do in the computation don't refer to previous values, so there's no reason to access them in this order. And so when I do it this way, so n is 0 for the inner loops, so 0, 0, 0, 0, and then I go to 1, 1, 1, 1, and so forth. And then I and j are also arranged in that way, so that I have 0, 0, 0, 0, 0, 1, 0, 1, and so forth. So you can see that now I'm accessing this element after element after element after element. And so this is much better locality than the previous example. Okay, does that make sense to everyone? Now we call this pattern of accessing memory the stride of the program. Okay, stride is about spatial locality, not temporal locality. Obviously, if you have temporal locality, you're going to actually have stride 0 because you're accessing the same thing over and over again. Okay, but when we have a program that accesses things in sequential order like this, we call it a stride 1 reference pattern. And like I say, you should think of stride in terms of the actual word size that the processor is using, how it interacts with memory, because that's what the processor is actually issuing to the hardware. When I access these things, and when I had the example before, each value is 4 bytes. And so it's accessing a D word, stride 1, stride 1, stride 1, stride 1. Okay. So yeah, like I say here, the updated version has a stride 1 reference pattern. The old version had a stride 4 reference pattern. Okay. And so we have this notion of stride K, where K is the element, or the space between the elements that we're accessing. So if we access every kth element, or as a specific example of our molecular dynamics program, if we access every 4th element, we call it a stride 4 reference pattern. Okay. And so we'll see some interesting examples. I have a program that you can actually run that traverses an array and slowly increases the stride that's used to access elements of the array. And it's really remarkable. You actually see the performance degrade as you increase the stride. It's a really remarkable thing, and you can actually plot it and get a sense of where your processor caches are, how large they are, and things like that. It's a really interesting thing. So 1D arrays, easy to achieve stride 1, but as you get up into multidimensional arrays, you have to pay just a slight tidge more attention to make sure that you actually achieve stride 1. And if you have programs that are really unusual, like you're representing graphs as a matrix of weights between weights between edges and so forth, and you're sort of hopping around that thing, it can be very complicated to achieve a small stride so that you can have a fast algorithm. And so that's where it can become pretty tricky. Matrix multiplication is also another example where you have to be a little bit careful to come up with a good stride. Okay, so we're adding SRAM between the processor and the memory, and we have a general sense of how our programs ought to behave so that it'll take advantage of this. And like I say here, accessing the SRAM cache is way faster than DRAM, but it's still slower than registers. Registers are also implemented with SRAM, but they're right on the processor. It's a very tiny memory. It's very close, so we don't have very far for the signals to propagate. And like I say here, we can access a register in 0 clocks effectively, where if you have an operation that's using registers, and it's only using registers, then it can be performed in 1 clock, so it's all performed in the same instruction. So the SRAM cache, though, can be up to 30 clocks away. It might even be further. It depends on the design of the system. But it may take that much longer to access. And, of course, if you throw the disk into the picture, you can see that as slow as we're making DRAM out to be, the disk is like a bunch worse. I was going to say 1 billion times worse, but it's not. It's like, probably, what would we say, like 100,000 times worse, something like that. So we don't like this. And even if you have a solid state drive, remember that magnetic disks are on the order of tens of milliseconds. Solid state drives are still on the order of hundreds of microseconds. So even though a solid state drive is 1 or 2 orders of magnitude faster than a spinning magnetic disk, it's still like maybe 5 orders of magnitude slower than DRAM. So we'd really like to use DRAM maybe as a cache for the disk, as well as using SRAM for a cache for DRAM, and so forth. And so it starts to give us this notion that, well, maybe we can actually extend this caching idea all the way through all the memory that we access. And so we end up with this memory hierarchy, which you see discussed in many different contexts because it's very important in computing systems. And we talk about it in CS24. We talk about it in the OS class because, hey, we actually build a cache for the file system. And we talk about it in database systems because the disk is the slowest thing the database can possibly touch. And so we'd like to keep data in memory instead of on the disk. So we have this memory hierarchy, and you can see that each level is, as we go down, is going to become slower, but it also becomes denser and cheaper. So we like it because we can store more information. But we start using each level as a cache for the level below it. Okay, so like I say, our CPU registers will cache data that would be in SRAM. Okay. Then SRAM is going to, and we have a couple of distinctions between on-chip SRAM and off-chip SRAM. The on-chip SRAM is always smaller, but it's closer and it's faster. Okay, we could make it larger, but then it's more expensive to build that processor. So then we have off-chip SRAM caches, L2 and L3. Frequently nowadays we have, used to be just L2, but now the gap is large enough that we need multiple steps between the processor and DRAM. Then we have main memory, and then we have local secondary storage, which would be our hard disks. This frequently we call external storage, because it takes a long time for the processor to actually pull that data back. And then we have remote secondary storage, which you could think of like Dropbox, Google Drive, the interweb, all of that kind of stuff.
Does that include like data center local remote drives? So like
yeah, I would say that it does. Anything that's accessed over a network, I would generally lump into L6. Now here we start getting really hand wavy too, because there's all kinds of crazy things that can go on in this picture that we haven't talked about. Who's heard of NUMA? Non-uniform memory access. So what you can do is you can have a cluster of computer systems, and you can map one computer's memory into another computer's address space. Totally badass. Basically, it allows you to do all kinds of information sharing between multiple computers in a cluster. The problem is that when the one computer wants to look at the memory that's on another computer, now you have to involve the network. That's why we call it non-uniform. Because now accessing this address is super fast because it's local. Accessing this other address is now remote. Okay, we can use the disk as a cache for the remote system's memory. Where does that fit into the picture? Kind of. But it fits in at the L4 level. That's the thing. It's actually, we're treating all of this as part of the address space, so it's like accessing L4. So you kind of have this thing where L3 is providing caching for L6 as well. Or something. I mean, it's weird how this all works. So there's a lot of ways in which this picture varies. Don't think that this is a set in stone, this is the one true memory hierarchy. I actually talk a little bit about this later. Actually, it looks like on this exact slide. Because there's other places that caches exist as well, like on the disk. Disks will have their own caches. If you bought a disk recently, if you actually threw down money for a spinning rust platter, then you probably saw that that disk has a cache as well. And that fits into the picture also. Okay? Because the disk will cache up reads and writes from the processor, which were cached in DRAM, and then it will go ahead and perform those reads and writes in the background, unless, of course, you want to force that data to the platter so that you can be sure it'll be around. Okay? You also have non-volatile RAM buffers, which are a little bit less common. This is for like high-end RAID controllers, which can log the reads and writes so that when the power goes out, it doesn't lose that information, even if it hasn't hit all the disks in the RAID array, and so forth. So there's a lot of places that you can have these memory hierarchies. Okay? So I don't want you to think this is the one and only true way of doing things, because it certainly is not. It's a general concept, this memory mountain, or memory hierarchy thing. Okie dokie. So level K has caching for level K plus 1. And you start to notice this interesting variation in how the various levels of caching are handled. If it's SRAM, then we're talking a very small number of clocks. We have maybe 3 clocks, 3 clocks. We have maybe 30 clocks versus 4 clocks versus 1 clock between various levels of caching. Maybe we get all the way up to 60 clocks. You don't have a lot of time to make a decision when you only have a difference between 4 and 30 clocks between 2 levels of caching. So clearly the hardware has to be very simple in how it manages the caches. And so you tend to notice that with the SRAM caches that the performance is critical, so we have very clever designs for how those caches are managed. Then you have things like DRAM being a cache for the disk. Well, in that context, you have a difference between like 20 milliseconds and, what are we talking, like 100 nanoseconds? That's a big difference. And so you have a lot of time to think carefully about what you're doing. And so the operating system has very clever and advanced algorithms and lots of interesting data structures for deciding what disk blocks do I want to keep and which ones do I want to let go. Because I can waste 20,000 clocks making a good decision to save myself millions of clocks. I want to do that. Okay. Same thing with the L0 cache, the CPU registers. Very limited resource. The computer doesn't think about it. It just executes the program. So you can think of the compiler as being the thing that assigns cache entries at the L0 level to cache information that might have been from L1. Okay, so it's just an interesting thing that you notice these various ways of handling caching at different levels. And part of the reason why is because you have different amounts of time that you have to work with at these different levels. Okay, so memory level K+1 is partitioned into fixed size blocks. That's one thing that you'll notice as an invariant as you go through these various things, is that the caching tends to work with blocks of a particular size. When you get down to L6, not so much. I mean, that'll be at a file level, and it'll be whatever size the file is. But when you go above that, then every level accesses the level below it in some block size. Okay, so like I say here, anytime data needs to be transferred between K and K+1, that block size is used. And it varies again, so between L0 and L1, obviously it's one register size or one word. L1 to L4, so anything involving SRAM is probably going to be using a uniform block size. On Intel, on x86, IA32, it is going to be 64 bytes. That's even true on x86 64. And then L4 and L5, so we're talking DRAM to disk, it's typically 4 kilobytes to 8 kilobytes tends to be the size. And again, if you think about it, reading 1 byte from disk is slow. But reading 4 kilobytes is only incrementally slower, just a slight tidge slower. So why not just read several kilobytes at once? So like I say here, we amortize that read-write cost over a larger amount of data. Okay, so we have this block size that's going back and forth. But that's not the only thing we need to keep track of, because we have to know if a particular space in our cache holds data. And not just that, but we also have to know where did this data come from. We have to have some sense of where that information came from. So that's what a cache line is. A cache line holds the block of data plus additional details that are necessary for knowing what that block of data actually is. So like I say here, a flag saying, does the cache line actually hold data? If the flag is false, then the cache line doesn't hold anything that we care about. Okay, so we can stuff something in there and then we'd set the valid flag to true. Tag that uniquely identifies the block. Basically, every block is going to have a way of uniquely identifying it. And then we have the block of cache data itself. So we would draw it this way. Okay, we have a tag that is some number of bits. I'll just call it T because it does vary based on our cache design. And then we have the block, which is going to be capital B bytes, and that's just a power of 2. So 2 to the lowercase b bytes. Okay, so that's a cache line. So the CPU says, I want data, I want to read this value, and the cache sort of sits in between, and when it sees the access for a particular value come in, it has to decide what to do. And if that line isn't loaded, or if I should say if that block is not in the cache in some cache line, then it turns around and pulls a whole block into the cache. So basically the cache is able to operate independently of the CPU to satisfy requests and do all of its management. So I guess here cache lines are slightly larger than B bytes because we have to store this tag and the valid bit as well. Okay, so the memory that sits behind the cache is divided into blocks. And so we have the example here, CPU requests a word in block 10. Hey, guess what? That's in there. Okay. Those are the block numbers in the SRAM cache. You can think of that as the tag. Okay. So in this case, if the CPU requests something and it's in the cache, we call it a cache hit because we hit the cache. Okay. The cache has got the data, so it's fast. We're at SRAM speeds, not DRAM speeds. Now if it requested a word in block 6, we're sad because it doesn't have it. So we call that a cache miss. And so the cache has to turn around and incur the performance cost of accessing main memory. So we tried, we failed, and the cache responds by just going and loading block 6 into the cache. Now, is that the only thing it has to do? What else do we have to do? Yeah, we need to write it to the cache. Where are we going to write it? So, yeah, the key is that we have to overwrite something. So we have to figure out which one of these currently cached blocks we're no longer want to keep around. We're going to get rid of it and store the new one. So we call that eviction or replacement. We have to figure out which one of these cache lines we want to evict the block because we no longer want it, and then we can load the new line into that. And so that is specified by a replacement policy, and caches have many different replacement policies. But the question that the policy answer is, when I have this situation that the cache is full and I need to load a new line into this cache, which line do I choose to evict? Okay, so that's what the replacement policy specifies. And here are a couple ones. There's some really fancy ones that are fun. I usually try to throw at least one onto the final exam just to expose you to a couple ideas. We go through a lot of them in 124 as well. But LRU, you may have heard of LRU. That is least recently used. You can imagine, just in your brain, because the cache is not necessarily going to do it this way, but you have some timestamp associated with each cache line. When was it last accessed, read or written? And when we need to evict a line, we just pick the one that's oldest, that's been accessed furthest in the past. It's actually a pretty good approach. It approximates the best policy, which we call the clairvoyant policy, where we always evict the line that is going to be used furthest in the future. It's called the clairvoyant policy because we can read the future. Okay. But then you could also imagine other policies like a random replacement policy where we just randomly pick something to evict and hope for the best. Okay. The thing to understand is that the choice of replacement policy does not affect correctness. It affects performance. And so we don't care as much about performance as long as we know the system is correct. Later we start caring about performance, but initially we really only care about correctness. Now here's another one. Are we going to have cache misses in this situation? The answer is obviously yes, because our cache has only invalid cache lines. So this is what we call a cold cache because it doesn't have any data yet. We actually call it warming up the cache when we start running the program, and its information starts getting loaded into the cache so that the subsequent memory accesses can be satisfied from the cache. But you can see from this that caches can have different kinds of misses. These are impossible to avoid. And so we also call them compulsory misses because they always happen. And you'll notice that when we simulate cache access, that you always have a certain warm-up phase where data starts getting loaded into the cache. You can't avoid those cache misses because the data simply isn't in the cache at all. Okay, so those are examples of cold misses or compulsory misses. And so this is another one of those things that you'll notice if you've ever done any performance benchmarking, or if you do in the future, which you almost certainly will, that a lot of times they'll have a warm-up phase where they'll just sort of ignore performance metrics during that initial phase because you're waiting for disk caches to get warm, you're waiting for hardware caches to get warm, and so forth. You're waiting for the system to get to a steady state, and then you can measure performance and it'll be useful. Okay, so CPU requests a word in block 5. So biggest part of the cache's work. We already talked about eviction and replacement. So let's assume that we're accessing something And we know as human beings, looking at the system from outside, that the thing being accessed is in there. But what is the problem that the cache has to figure out? Yeah, is it in there? And if so, where is it? That turns out to be a little bit complicated. So this is dictated by a placement policy. The placement policy basically says where cache lines, or I should say where blocks go, because the cache line is in there, it just holds blocks. So where does the block get placed in the cache, with the presumption that if I make choices or make constraints about where I place things, then maybe that'll make it a little bit faster to figure out where it is. So the most flexible placement policy is anywhere. I can put it anywhere. Okay? So that's a random placement policy. That also is the most expensive because the cache has to have logic to go and look at all the cache lines to figure out, does this cache line have my block that I'm looking for? Does this cache line have my block? And obviously it can do some really clever stuff with like an n-way parallel equal comparison so that the one cache line with the data will say, I'm here, I have it. Or nothing will turn on and you'll say, okay, it's not in you. So you can do that in constant time, but it takes a lot of gates. And so that makes things slower, remember, and it takes more power. And so we'd like to avoid doing that if we possibly can. Okay, so that is the most expensive placement policy. Obviously, if you're doing a software cache, then you can use a hash map or something like that. That'll make it very fast. And so you'll typically see random placement in software caching because we can do that. It's super fast. So hardware caches, trying to constrain this problem so that logic doesn't get too complicated or too slow, uses pretty strict placement policies where basically you have some subset of locations where a particular block is allowed to be stored. And that subset of locations is chosen by the block's address. We use the address because that's an easy value at hand to figure out where to actually store the value. So cache lines are grouped into what we call cache sets. And when you have a block from the lower level, it can only map to one cache set. It's not like you can map it here for some of the accesses and then you map it over to another cache set. Every block is constrained. I can only store this block in this cache set. It's hard-coded, hardwired into the hardware. Okay. And so like I say, if the cache set contains multiple cache lines, I can put it in any line in that set, but now I've sort of constrained the problem of figuring out which line holds it because I've said it's got to be just in the subset of the lines that I have in my cache. So there's two extremes that sort of emerge from this. We have S cache sets, so we have a whole bunch of cache sets, and each one only has one cache line in it. That's super fast. It's just like imagine that you had cubby holes, and every single thing that you owned, you put in the exact same cubby hole every single time. I always put my keys here, I always put my phone here. You always know exactly where to look for stuff. Then the other extreme is I have one cache set. This is kind of how I manage my life. One cache set, and that has all the lines, and so you can put anything anywhere in it. So now you have to look at every place before you can figure out if the block is in there. So we call these the number of cache sets S. This will become more important in a second. And we have how many lines are in each cache set. That's E. All cache sets have the same number of lines in a particular cache design. Okay, so let's see. Yeah, so this is every block maps to exactly one set in the cache at level K. This is the way that we do this. You can see that, yeah, so I'm not going to talk about that yet. We'll get into that in a second. But we have direct map caches. This is the one extreme. Direct map caches are where each set has only one line. So it's very easy. We just figure out what set, that's a line, it's either in there or it's not. We have one tag to look at. If it's not in there, we can go ahead and evict it. Replacement is super easy as well because I only have one choice where it can go. So I have to evict the old guy to put the new thing in there. Fully associative cache is one cache set which contains all E lines. Okay. Because of the thing that we talked about before, you have to look at all of the tags. And so this is also why we call it an associative cache, because we look up the block not based on address, but based on the tag that's associated with the block. It could be in any position in the cache, so we use the tag to look up what it is. You can think of it as like a hardware hash map. if you will. Okay, direct map caches. So now we're saying that we want to map each block to a single cache set, and each cache set can only have one cache line in it, so we are in effect mapping every block to exactly one cache line. We can now have new fun ways of missing data in our cache when we want to access it. So let's say that we have 4 cache sets in our cache, just like I have indicated here, numbered 0 through 3, and we map blocks to cache sets based on the block's address, if you will, modulo 4. Okay, so obviously that'll give us 0, 1, 2, or 3. That'll tell us which set, and we can go ahead and look at it. And you can see, for example, that 10 mod 2 is 2, so it's in set 2. 8 mod 2 is 0, or 8 mod 2. 8 mod 4 is 0, so that 8 would go in set 0 and so forth. So everything is in its own cache set where it's supposed to be. And then we have a program that for some crazy reason decides I'm going to have really good spatial and temporal locality, and I'm only going to access stuff in blocks of 9 and 13. Yeah, that is one way of putting it. But yeah, basically we have a problem now that the cache is going to look a lot smaller than it actually is because of our placement policy. Every access is going to go into the same cache set, and the cache set is much smaller than the whole cache, so we end up with another kind of issue. So every time, let's say we're just toggling back and forth between 9 and 13. Every time you make that request, it's going in cache set 1. But every time it's not going to have that block. We call these conflict misses because they are a conflict between the placement policy and the access pattern of the program. These are terrible. They're very difficult to work around. Thankfully, most systems don't have direct map caches anymore because hardware is getting very advanced. We had direct map caches back when I was a kid, back when I was a frosh, whatever. But they're a lot less common now. Okay. So you see here, placement policy constraints and memory access patterns, you have a conflict and you get a lot of cache misses. So we call this thrashing. This is one area where you can get thrashing. And it's going to make the program run basically at the speed of main memory, even though you have available cache lines that are not being used. You have great locality, and you have plenty of space in your cache, but nonetheless, you're still ending up with DRAM access speeds, not the cache access speeds. Okay, questions? It's very hard to design this problem out of systems. Thankfully, the hardware has gotten good enough that we don't have that anymore. I'm trying to think if there's anything else I want to say about this. Not right now. I don't want to go into any more detail right now. Okay, yeah, so we have caches designed to work against the main memory with capital M bytes. So we say we need lowercase m bits to represent that m bytes. Now, obviously, m is going to be a power of 2 to make this all work easily. And so we have these various parameters, which we've been using, but we're going to sort of formalize it now. So capital B is the number of bytes in each block, which is 2 to the lowercase b. Okay. And then S is the number of cache sets. Lowercase s is the number of bits we need to represent the set number, or the set index. And E, cache lines per set. So if E is 1, I have a direct map cache. If S is 1, then I have a fully associative cache. Like I see here, S and B are both powers of 2. E can be whatever we want. And so our cache can store an amount of information that is the product, basically, of all of these things. So B is the number of blocks in each line, or blocks, number of bytes in each block, and a block corresponds to a cache line. And then we have E cache lines per set and S set. So we just multiply those all together, and that tells us the size of our cache. Okay. Now that's not all the space we need, because we need to keep track of the other details. The tag, we need to keep track of the valid flag, but we don't really count those in the size of the cache. We care more about how much data can actually be stored in the cache, not the additional bookkeeping details. So we take a memory address, the processor sends out a memory address, it hits the cache, and the cache has to make some decisions about, okay, what cache set could this be in? What's the tag so that I can look in the cache lines and see if I have a line with this value in it? Okay? So it has to figure all these things out. And so it takes the address bits coming in and maps them to those things as follows. Okay? The bottom B bits are always for the block offset, because if I have, let's say, a 64-byte block, then I can basically, what is it, the low 5 bits? I can't remember my powers of 2. No, it's got to be the low 6 bits. Am I right? Somebody help me out. 2 to the 6 is 64? That sounds right. I'll go with it. So anyway, so the bottom 6 bits would be the offset within that block of the actual byte that I want. Okay, so I need B bits for that. So for example, if I had 64-byte blocks, which is what IA32 uses, then that B would be 6 bits to say the offset. Okay. Then I have the next S bits, which is just the log of, the log base 2 of the number of cache sets I have. That's how many bits are necessary for identifying the cache set. Okay. And then the remaining bits are the tag. Okay. And you'll notice that the way that this is designed, every block that maps to a particular cache set has a unique tag. 2 different blocks can have the same tag, but they'll map to different cache sets. Very important to understand. All of the blocks that map to a particular cache set have unique tags. So that when the hardware cache is trying to figure out if the block is in there, it can just look at the tags to figure out whether or not that block is actually in that cache set. Okay? That's a very important detail to understand. It'll make a lot more sense if it doesn't once you do assignment 5, because you really have to figure that. You have to do all this stuff manually. So why do we use the middle bits for the set index? Well, I don't know if anybody's looking at last year's slides, but I'll just show it to you. Basically, if we had the topmost bits for the cache set index, then you can imagine that you're going to have long sequences of blocks where all of those blocks map to the same cache set. And as we're trying to exhibit good spatial locality, or I should say spatial locality, we're traversing an array. We have all kinds of stuff going into one cache set and then a whole bunch of stuff going to the next cache set and so forth. We don't want that. We want the cache sets to be as distributed as possible. So if we had a situation with 4 cache sets, M was 16 bytes, so we only have 4 bits for addresses, 4 cache sets, so the top 2 bits will be to identify the cache set. You can see that, well, top 2 bits, 0, 1, 2, 3, all have the same top 2 bits. So all of those first 4 bytes go into the same cache set. That's pretty lame. But if I use the middle bits, then I get my values distributed across all the cache sets more uniformly. And so that way, if I'm just traversing data in memory, it's much more likely that accesses are going to go into different cache sets. Okay? So this is an example of trying to optimize the common case, the choice of the set index. Okay? Any questions? Okay. You will understand this after assignment 5, I guarantee it. Okay, so cache receives a memory access. It has to do these things. Figure out the cache set where the block goes. Hey, that's easy. I just take these bits. I have to figure out which line matches the block. Well, that's easier because now I just look in the set. If it's direct map cache, it's super fast because I just look at the one tag. If it's associative at all, then I have to look at all of the tags in the cache set to see if there's anything that matches. And then access a specific value within the cache block. So I use that offset to do that. So you can see that these steps are pretty easy. Okay, I already talked about the set index. I just used that to figure out what set to look in. The tag bits identify the line within the set. And you can imagine how to do this all with logic. We're going to be doing it with a program on assignment 5. But you can imagine that the set index could be fed into a decoder that would activate the appropriate cache set and deactivate everybody else. The tag could go into this n-way comparator to have the cache line that actually has a matching tag activate and say, hey, I've got it, or nobody activates and you know that you have a cache miss. So you can imagine the way that this could be constructed very straightforwardly in logic. It takes a lot of logic, but hey, it's really worth the savings, the performance savings. Okay, so direct map caches, they have S sets. Each set only contains one cache line. So this is easy. We have a lot of bits in our set index, so you can see that S is going to be larger. So that makes us happy. And the easy thing is we have basically a one-to-one comparison. Is this block actually in the cache set that it maps to? I just look at the one tag that's already in there. Obviously, I look at the valid flag as well. If they don't match, I need to evict that block and load the new one. Okay, so fast to map an address to a cache set. Fast to say that 5 times fast. Fast to determine if a block is in the cache. I just have to look at the one tag of the cache line in the set. Okay, that's direct map. Fully associative. Notice I no longer have cache set bits. Because I have how many cache sets? 1. Well, 2 to the 0 is 1, so I don't need any bits for the cache set index. All of the remaining bits are tag, which you can already start saying, oh, okay, well now my comparisons are also more expensive because I have more bits that I have to look at to have unique tags. So this would be an example of a fully associative cache. One set, and I have all of these lines in that one set, and so it's fast, obviously, to map an access to the cache set because they all go into the same cache set. But then if I have to figure out where does it appear, which line, then I have to look at all of the tags at once. Okay? And the tags are larger. So you have 2 strikes against you when you have a fully associative cache. All right, questions? Okie dokie. So we have these 2 extremes again. And we have 2 ways of solving this problem. Thankfully, we kind of have this cool knob that we can turn. We have direct map caches on one end, which are really easy to implement, but we have conflict misses galore, and that makes our programs slow, and it's very hard to design those issues out. Then we have fully associative caches, where the cache is really complicated. Programs love them because I have no conflict misses. It's as efficient as it possibly can be. So we have a blending of the 2, which is set associative caches, where we have more than one cache set, and we also have more than one line per set. And it turns out that you can have not too many lines per set, and it behaves pretty well as far as conflict misses are concerned. We can basically eliminate thrashing by having 4 or 8 or 16 lines per set. And that's a much easier hardware design than having all of the lines in one set. Okay, so like I said, it greatly reduces the potential for conflict misses, and it limits the complexity of the logic that you have to deal with. Okay, and again, I think you'll get to see an example of that on the 5th assignment. Okay, so here's an example of a 2-way set associative cache. So when we say 2-way, that 2 is E, so we're saying that there's 2 lines per set. You'll notice that we don't really say how many sets there are. So if we said 16-way set associative cache, what we're saying is there's 16 lines per set, but we're not saying how many sets there are. So you'd have to also say with 512 sets and the block size is 16 bytes. So that would be a full specification of a cache. Okay, so let's see. Set associative cache. So yeah, we have E is 2. And so an M-bit address, since we have 4 cache sets, and again, that's not in the E-way set associative cache part, but we have 4 cache sets, so we need 2 bits to specify the set, and then the rest of the bits are used for the tag, and we can check 2 lines. That's pretty cheap. Okay? Questions? All right, let's see. So set index to find the cache set, and you only have to check a small number of lines. So when you have set associative or fully associative caches, then you do need to think about the replacement policy. Okay, so a cache miss occurs, you have to load a new block into the cache, so you have to store it into some line, but you have to store it in the same set, just like before. Direct map caches don't have this problem because you don't have a choice. But yeah, set associative and fully associative caches, you have to make that choice. Okay, so we already talked about that. Least recently used. There's another one that's interesting, least frequently used, where you have some sliding time window and you look at what was accessed most frequently in that window. Okay, so that's another approach that you can use. There's a few other ones as well. There's actually a really clever approximation of least recently used called aging that does a really good job of estimating which line is the oldest, but it quantizes the history so that it's not precise, but it's still a pretty good estimate. Okay, they do take extra hardware to implement. Like I say, typically not used very much in hardware caches because you want that thing to be as fast as possible. The more logic you have, the slower it's going to go, and so forth. Okay, but where you start getting further away from the CPU, like in the operating system, then you definitely start giving it more thought. Okay, I already talked about this. Cache miss costs 20 million clocks. You're willing to spend a few 10,000s to figure out what's the best thing to do. Okay? Let's see. Associative. So I already talked about this as well. This is an associative memory. We don't use an address to look up. I mean, in a sense we are, because we take that address and we map it into various things. But really, we're taking a tag which doesn't specify the address of the value, and we're using that tag to retrieve the value instead of an address. So that's why we call it associative cache instead of, sort of a typical addressable cache or addressable memory. Okay, let's see what else to say about this. Okay, yeah, so basically what this is saying here is that one thing you can do to sort of simplify the design is include the valid bit in the tag that you're looking at, whereas the incoming tag always has a valid bit of 1, because you're like, yeah, I want it to be there. And so you can lump that in as well, and that makes it easy to design the cache, the mechanism that identifies whether the line is actually present or not. So that's an easy thing to do. There's other ways to do it as well. Okay, I think that I don't really want to talk about any of this stuff. Okay, any questions? All right, we'll see you all on Monday.